Okay, so this is a video I said I would have made for my friend Mike. He wants to get into field theory. He wants more mathematical videos. So this is going to be a good introduction video for two series I want to start on, right? So I want to do a series on bohemian mechanics, right? Which talks about a different interpretation of quantum mechanics, which also starts from this same starting point. And then, of course, quantum field theory, which also starts from this same starting point. So this is going to be a general video, and we'll go from there, right? So the first thing we're going to start off with is a lot of modern physics comes from this concept of energy of your system, right? And knowing the energy of my system, how can I know about what are known as the equation of motion? How can I know how my system will move through time, usually? And so we start off with this function known as the Lagrangian. And Lagrangian is defined to be your kinetic energy, which we call T, minus your potential energy, which we call V. Now, in the past, if you're like new to modern physics, or you just took, a freshman physics class, or, Newtonian mechanics, really what you know back then is this T is known as, KE, and this V is known as U, right? These are the same thing, right? So when I took this class many years ago, I remember when we got to this point, the guy was like, now we're upgrading to the big boy notation. You're going to be writing T instead of KE. I was like, wow, how amazing, right? And we'll talk about other stuff I was confused about from that class, but we'll start here, right? And so naturally, you're going to wonder, okay, man, what is, this is a function you tell me? What is it dependent on, right? And so in the modern textbooks, you will see that the Lagrangian is dependent on your coordinate over time, you're changing the coordinate over time, and your time, right? In other words, your Lagrangian is dependent on, I'll use modern notation, right? Well, technically not modern, but that's fine. Oops. Right? Technically it's not modern. We're not going to go straight into field. It's just a primer for that because bohmian mechanics doesn't really go further than this. It's relying on your position, your velocity, and your time, right? Because if you look over here, your kinetic energy is reliant on your velocity, right? Because it's kinetic energy is defined to be how much energy it takes to take your object from zero velocity to its current velocity, right? That's the definition of kinetic energy. It's an integral of work, right? And so your potential is usually dependent on your position, right? How an object moves is usually dependent on the background potential and free of forces, right? So that's why this one usually depends on position. This one usually depends on velocity. So you can see how your Lagrangian function can depend on these things, right? And we'll just talk about the notation here real fast. X of t in your Cartesian coordinates now becomes this cool new fancy Q of t because of generalized coordinates. And so we have to stop and ask ourselves, well, why, right? Because if you think about it, the universe does not care about which coordinate system you use, right? The universe can't care. Coordinates should not have a matter and a say into anything, right? It might be easier for us, the human, to say calculate, something in spherical coordinates or cylindrical coordinates or hyperbolic coordinates or Cartesian coordinates, right? But the universe don't care, right? The universe can't care, right? So coordinates do not matter. So this x of t becomes q of t, and then of course, the derivative of our position with the time becomes this cool new fancy x dot, or in this notation, q dot, right? This is just notational stuff, just so we know, right? You may have seen this before as v, velocity, right? But this is just notational stuff, right? So this is the Lagrangian, and so it's defined as the difference between your kinetic energy of your system and your potential energy of your system. Now, you may have heard of something called a Hamiltonian, and some people will say the Hamiltonian is known as the total energy of your system, quote unquote. Wrong, 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 right? Why is that wrong? Because that's not the full definition, right? The full definition involves going through what is known as what is it called? Not Lagrange. I don't know, Lagrangian. I'll spell it out. I think. Le Grand. Yeah, le Grand. No, le Grand. That's Grand is G-R. It doesn't matter. Whatever this guy is right now, I can't think. This transformation is a transformation that involves the derivatives of your systems, right? It not necessarily your system, because it's a mathematical transformation. It involves a transformation using your differentials. That's a better way to say it. And so let's quickly talk about this function a little bit deeper. What I like to call this as, and I don't know if it's official or not, but I like to think about this as my state space, because this tells me all the possible states I can be in, right? And so the Hamiltonian relates your momentum to your coordinate. So we go into a new space called the phase space, right? Meanwhile, this one relates your velocity to your coordinate, right? So in my head, using this transformation, I want to move away from this velocity dependence, and I want to sucker in this momentum dependence, right? And so I'm going to be fancy with us for a second, and I'm going to write down a definition. We are going to write down the momentum conical to the coordinate P, right? So I'm just going to write it down here real fast. Right? Okay. So when I took this class when I was a freshman, I remember we got to this point, and I remember hearing that phrase: the momentum conical to the coordinate Q. And I was like, oh my God, I was already drowning at this point, right? We're mid semester. I'm floundering, right? It's my first semester in college, and we get to that point. I'm like, man, I'm super out of my depth. I've never even heard of that word, conical. What the hell? And no one else batted an eye. I didn't even ask. I was like, oh my God, I must be so dumb. I'm so behind. I don't even know what conical means, right? So let me save you that worry that little me had. It just means rule or standard. It comes from the word, this Greek word called konon, which just means rule or standard. So all this means is momentum conical to the coordinate means I'm going to define a rule that relates my coordinate to my momentum. Very simple, but sounds fancy, right? So that's all this is. So this is actually a definition, right? So now, remember, I want to use this. I want to use this in replacing this, because I want to relate my momentum to my coordinates. So we have to think. This Lagrange transformation involves relating our differentials. So the first thing we're going to do is, well, I want to get rid of that Q dot, and I want to bring in that P. So I'm just going to make a function, right? And I'm going to take the differential of it. So let's do that in blue, right? So we're going to say, okay, cool. This D, make sure I'm running the ball good. This D of this guy, I want to get rid of it. And I want to bring this guy in. And so we're just going to do a, what is this called? Not a chain rule, a product rule. We're just going to do a product rule, right? And so we take the derivatives, and we're going to get P dq dot plus P, Q dot dP, right? Not that big of a deal. And then we're also going to take the derivative of this function, right? Because I want to get rid of this Q dot, and I need to find a relationship, and this is the only thing I know that has a relationship with that Q dot, right? And we're not going to use this guy because we'll use that guy later when it actually matters. But for now, we'll use this guy, and we'll take the derivative of this. So let's ask ourselves, what is the derivative of this L? So I see dL is equal to, well, I'm going to have to do what's known as a chain rule, right? So I have a dependence on this Q and a dependence on this Q dot. So if we do that, we will get partial L, partial Q, dQ, plus partial L, partial Q dot, dQ dot, right? And so let's pause for a second, right? What is the definition of momentum, of this conical momentum? Partial L, partial Q dot, right? And remember, this I right here just means like which direction. So you have to pick one. Over here, we're taking away indices just to make our life a little bit easier. If I haven't done that so far, I don't know why I randomly did that over here. Just happened, right? So we look over here and say, oh, cool. I have I have a relationship. Bam, bam. right? So I'm going to rewrite this. And since it's an addition, maybe see where we're going with this. Because of addition, it doesn't matter which order I write it in. So I'm going to switch the positions of these two. So I'm going to get this as P dq dot plus partial L partial Q dp. Okay, so let's see what we can do here, right? If we subtract these two equations from each other, what do we get? Right, that's the beauty of this method, right? If we subtract these two equations from each other, what do we get? Well, over here, I will get, d. Actually, we'll talk about that in a second. There's a shortcut we can make, but we'll talk about what I don't want to skip ahead for you guys. Well, this one and this one just cancel, right? And then over here, I get this q dot dp minus partial L partial Q dp, right? So we, from here, can invoke a rule, right? From here, we can invoke a rule. And that rule that we're going to invoke is, it's called the linearity of linear operators. Sounds fancy. It's not that fancy. Essentially, all it means is like, if I were to take the derivative of, x plus y, this is necessarily the derivative of them each individually, right? This is just simply equal to dx plus dy. Now, it's not just for this. It's usually for most binary operators, right? So we have an addition over here, but look over here. I have a subtraction sign, right? So I'm going to invoke this one, but backwards. So I'm going to rewrite this guy right here as the derivative of q dot p minus L, right? Is equal to these guys over here, right? Doesn't matter what it's equal to, right? So we are going to integrate both sides now. Actually, I guess I'll write it out for us. Right? We can integrate both sides here, right? And which side's easier to integrate? Obviously this one, right? So we're just going to sit over here and say, cool, this is equal to q dot p minus L. This is actually the definition of a Hamiltonian, right? This is just junk over here, which I can just define to be h, right? You can integrate it. It doesn't really matter. You'll get that these are equal to each other. So we define this to be the definition of a Hamiltonian, and the Hamiltonian is dependent on our position and our conical momentum, right? And so that is the definition of a Hamiltonian. It's not the total energy of your system, right? So, but you will see people who will write down the Hamiltonian simply as h is defined to be t plus v. And we'll talk about that, why that is right now, actually. So I'm going to erase all this. So this is the definition of a Hamiltonian. So I'm going to erase some stuff here real fast. Because we just applied our transformation. We derived the Hamiltonian, starting from the Lagrangian. You're caught up now, right? So go back in the video if you need to watch it. It's not a live lecture. So okay, so now, why do people call it the total energy of the system, guys? Well, let's just do a quick example. What if we're working in Cartesian coordinates, right? So, and we have no potential. So we say h of our q, p is equal to this q dot p minus L. And once again, technically, we should have this depending on how many coordinates we're working in, but we'll move that for now, just make it life easier. And let's say we're working in Cartesian coordinates. Let's see what we get. So in Cartesian coordinates, what is kinetic energy? Let's write down the Lagrangian. Lagrangian is 1/2 mv squared, right? Or I guess technically, as we're working with this new notation, we're going to write this as x dot squared. And then what is momentum in Cartesian coordinates? Well, momentum in Cartesian, actually we don't even go there. We can use our and we can keep, let's even keep a potential here. Why not? That's dependent on just our position over time, right? And so now we can write down our conical momentum. Our conical momentum is the derivative of our Lagrangian with respect to this x dot, right? To our velocity in our coordinate system, right? Remember that q dot now becomes x dot. You guys see that, right? So let's do that. Well, remember, our potential does not depend on our velocity. It only depends on our position. So if I take the derivative, that one just goes away. And this first one just becomes mx dot, right? Well, you probably have seen that before. Remember, for linear momentum, I believe it's simply just usually written down as mv equals p. Wow, we just derived it, right? So cool, it works. That's pretty cool. So that's just, gut check from your Newtonian stuff. So we get this. So now we have to write down our Hamiltonian for our system, right? And so I believe, actually, if I remember correctly, usually you're going to want to multiply by -1. I guess we'll see in a second. Sometimes when you do the derivation fast, like I just did, sometimes you need to multiply by -1 to get the total energy of the system. So we'll get to it in a second. So let's just write this down. So Q dot in this system is just x dot. P, which is mx dot. And our Lagrangian is simply just 1/2 mx dot squared, right? And so from here, we can write this as mx dot squared minus 1/2 mx, oops, and I forgot my Hamiltonian. Sorry, my potential minus v of x comma, oops, let me just, should have written that a little bit better. So we'll just write this over here, p is equal to partial l, partial x dot is equal to amx dot. Okay, so, and I forgot to write my potential over here minus, plus, because it's minus, so it's minus over Lagrangian, so it'll be a plus over here, plus our potential, like that, right? Cool. So we have this now, right? And so now, okay, cool. So we have a full mx squared minus 1/2 mx squared. This is just simply going to be equal to 1/2 mx dot squared plus v of x comma t. And huzzah! What is this? Total energy of our system, right? But that's not true for every coordinate system, right? So when in doubt, if you were ever asked the question, what is the Hamiltonian? Right? You're asked that question, do not respond with total energy system, do not respond with this, and in part respond with this. Hopefully that makes sense, right? This is a stickler though, right? You can get rid of this in casual conversation, but if you're in a more technical thing like we are right now, you have to write this as your Hamiltonian of your system. And then, like I said, a quick note. When you're actually doing the transformations, there have been times, if you go fast like I do, you may forget the order, right? It doesn't really matter the order. You want to write it down this way so you can get this to pop out. That's like a quick check for myself. But sometimes when you're doing the transformation, like if you do it on your own, depending on the order you subtract, like for example, if I did dl minus d of pq dot, I would have to multiply by -1. Do you see why? Because they change. Does it really matter? No, because when you're doing this equal over here, just multiply by -1 in that step, it's mathematically correct, right? So, okay, cool. So we derived our Hamiltonian from a Lagrangian. What can we do next? Okay, so the last thing I guess we'll do is let's derive from Hamilton's principle what is known as your equations of motion for your system, right? And so these are known as the Euler-Lagrange equations, right? And so it's been a minute since I derived them, but let's go for it. So essentially for the Hamilton's principle, it states that the variation of your path has something very important. So essentially the way I like to view this in my head is the following. Let's say I ask, what paths will my system take between these 2 points, right? And this is in our state space, right? So this is dependent on our q and our t, right? So this is all the possible states that my my particle can be in. Actually, that's just position space. I'm getting ahead of myself. I'm just in position space right now. And so from here, you ask yourself, what path will my system take between this q naught, t naught, and this q, t over here, right? And so I like to think about this as the following thing. It comes almost from, once we get into those quantum fields and we get to these Feynman diagrams, we get into the concept of sum over histories, but it comes really from this, and Bohemian mechanics has the same thing. We know in the real world, our particle just takes one path technically. Our system just takes one path technically, right? But that's in the classical world. And so the way I like to view that is, okay, in normal space, it's just a straight line, right? If we're working in our place right now with no potential, just yada, 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 usually a straight line. But could it have taken this path? Let's write in different colors. Could it have taken this path? I guess. Right? I guess it could have, right? Couldn't it have taken some path like this? Sure. It didn't though, right? So how do we know what path it took, right? And so we use what's concept, this Hamilton principle. And so the most important thing, and I guess in a more rigorous video, I will go through the epsilon arguments, I guess, even though I don't like them and they don't make too much sense to me. I can do it, right? So, but for now, all we really need to focus on is that it's a path. And so these paths, they may, from here to here, I have a difference in position. Here and here, I have a difference in position. Here and here, I have a difference in position. Here and here, I have a difference in position. Like, I have difference in positions, right? But they don't matter at my ends, right? And so in order to do these things, you must understand that principle. That necessarily, mathematically, what we're going to write down is this. And so this delta means variation. And we're saying our path doesn't vary at our endpoints. It's just zero, right? But let's say I picked some random thing right here, right? Here they would vary, right? At this point, all my paths would vary, right? And so it would not be equal to zero at those points, right? And so what we are going to calculate is essentially this thing. The path my system takes will be extremized by this formula. Okay, so this is just a derivative, right? So we set it equal to zero because that comes from those concepts, right? If I extremize something, my derivative better be equal to zero, right? Okay, so let's go ahead and just do that real fast. All right, let's see if there are equations. Let's solve this stuff right here. So if we do that, essentially what we have is we're going to be varying, or taking, in my head, I'm just taking a derivative. I'm just taking a derivative. That's the way I think about it. So we're going to say this delta L of Q dot T, right, equals zero. Sorry, this integral of this equals zero. And I should have a dt here. And this should be equal to zero, right? So let's do a chain rule, right? So the first thing we're going to do is a chain rule, right? So this, instead of writing as d at the end, I'm just going to write it as delta whatever. So the first one we're going to do is going to be partial L, partial Q, delta Q, plus partial L, partial Q dot, partial Q dot. All being integrated over T. I mean, this thing with respect to T. And of course, I should have been more blatant. Sorry, I'm just going for myself at this point. Remember, you do have an initial position in time. So don't forget that. All right. technically over here too. Oops, and that's like a Q. Cool, right? So now we're going to be invoking that property of linearity again, right? Remember from the derivative case, we had that property where if I have a linear operator such as a derivative or integral, they have this property. This property is that I can split this apart, which I'm going to do. So I'm going to split this apart into two different integrals, right? Because maybe if I handle them one at a time, it'll make my life easier, and it does. So remember, integrating this from, I'm just going to write this to make my life easier. Partial L, partial Q, delta Q, dt, plus partial L, partial Q dot, delta Q dot, dt. All right, that's all equal to 0. Cool. And there's an integral here as well. Forgot about that. From Q naught to Q. Cool. So let's take a look at the second one. And in the second one, we're going to be integrating it by parts. Because that's really the only technique we can, if we have a chance at integrating this, right? At this point, integration of parts is going to work. I don't see U substitution working, right? If I took U to be delta Q dot, nothing's going to happen. If I take U to be that, nothing's going to happen, right? So we're going to be integrating this one by parts just to see if we can, right? So let's just get our integral ready and let's ask ourselves, which one of these is easier to integrate? And you might be perplexed. You might look at that one and you might say, ugh. Well, I guess if I integrate that first one, I get L, but how do I necessarily differentiate that second one? And so I'm going to teach you a trick that you know about, but you don't necessarily use a lot. Actually, you do use it a lot. So I lied about that. It's something that you use a lot, but even worked in this field for a while, you don't really use it often. It's the fact that mixed partials commute. Right? So what does that mean that mixed partials commute? It necessarily means that the order of differentiation doesn't matter. And it shouldn't matter if you think about it, right? Why would the order of differentiation matter? So I call that concept mixed partials commute. In a more rigorous video, I'll talk about why I call it that, but for now, we'll just call it mixed partials commute, right? And so I can rewrite this term, right? This delta Q dot, because this is a derivative, but this is also a derivative. So you see what we're going to do? It doesn't matter which order I do the differentiation. So this Q dot technically is dq dt, right? So I'm going to switch the order of the differentiation. So I'm going to rewrite this as d of dt of this delta q, right? Mixed partials commute. Now, I'm going to let that be my dv. Why? Because when I integrate it, ddt just goes away and I'm left with v equals q dot. So let's try that. dv equals this, so then v is just equal to delta q, right? Now, that must make my u equal to this junk, partial L, partial q dot, right? So then necessarily what is du? Well then du is equal to the time derivative of this function with respect to time, right? Looks messy, and it is. It looks pretty junky, right? But that's the way I write it because it makes sense to me. So now our integral is going to be uv. Actually, technically, I wrote that bit too early. So technically, our integral is going to be this uv, which is going to be partial L, partial q dot, delta q from our initial position to our final position, which is going to come into handy when we get there in a second, minus our integral v du. So minus this junk partial L, partial q, dt, partial q. Okay, looks like junk because of this. Let me just write that better, real fast. Okay, looks like junk, whatever, right? So, we're almost done, we're almost there. So let's ask ourselves, what does this mean? By definition, 0. Why? Give you a second to answer. Dun, 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 dun. this guy doesn't vary at endpoints. Therefore, the variation of Q when I evaluate at Q0 and Q is 0. So all of this just goes to 0. Now I'm left with this junk here, right? So I'm going to rewrite this up here, right? I'm going to take all this away. And hopefully I remember. Where was that? Luckily, I think I have a good memory. So we're left with this variation of our path, right? And so we did integration by part on our second term, but we still have that first term there. So we're still going to have that first term, which is from Q0 to Q of partial L, partial Q, delta Q, right? And now we're going to bring in that second term, right? The second term, the VDU that we had, right? So this is going to be the integral of Q0 to Q of that VDU. That VDU was what? D dt of partial L, partial Q dot. I'm sorry, there's a dt here too. Don't forget that, my bad. And this one's going to be dt partial Q. This has to be equal to 0. Don't forget that. So let's pause. Do these guys have, because I want to recombine these integrals, right? So if I were to recombine these integrals, is there anything I could factor out? The answer is yes. I have a delta Q dt here and a delta Q dt here, right? So I'm just going to factor out of both terms, right? Now, something I've questioned, something I don't really have an answer to, but now that I bring this up, how does this relate when I invoke, wedge products and all that? That's a good question. I'll have to think about that. Thank you for that question, audience member. Because and I'll just take a little quick detour, right? When we get into exterior calculus, this concept is actually equal to negative dy dx, and this is due to the anti-symmetric property of a wedge product. So a wedge product would say this technically is dy dx d wedge dy, right? And the anti-symmetric property of that means if I were to switch the order of these, this product has the property that is equal to this, right? So I wonder, because up here, technically I am switching the order, what does that necessarily mean? Maybe for this space that we're in, it doesn't matter. I will have to look into that. But for now, what we're going to do is, of course, I'm just going to switch the order of this, right? And because I switched the order of this, I can factor it out, and I'm left with this. Of partial L, partial Q, minus dt all factored by this partial Q dt equal to 0, right? And so now I'm thinking about it. Now that I'm thinking about it, right? Usually you will see this written as d dt partial L partial Q dot minus partial L partial Q is equal to 0, but really doesn't matter because of the 0 here. The order that we write these in truly doesn't matter in my opinion, because it's just math at the end of the day. So this right here is the main story. I got too stuck on my own question that I randomly generated while doing this. But this is what is known as the Euler-Lagrange equation. So this will tell you the path your system goes in. And so that's it, right? It's not too much. Like I said, this is the first video for Bohemian and both field theory. So, a quick question we can ask ourselves is, let's do a harmonic oscillator. One of the physicists' favorite ones, not my favorite, but physicists' favorite ones, right? And let's see if we can use our equations to find our equation of motion. So let's just do it real fast. So what is, and let's just do it for a unit frequency. So there is no frequency involved in this one, it's just an oscillator. So the Lagrangian for an oscillator is just the potential, it's the kinetic minus potential. So the potential for oscillator is always going to be 1/2 x squared, right? Because that depends on this position. And we're going to be working in Cartesian coordinates, so we have x. And so the kinetic energy of an oscillator, I think, is always going to be 1/2 mv squared, or in our new notation, x dot squared, right? So the Lagrangian for this is going to simply just be L is equal to 1/2 m x dot squared minus 1/2 m x squared, right? So then our Euler-Lagrange equations, which, involve talking about differentiating this Lagrangian with respect to our position, which is just x in this position. Well, if we do that, we get mx, right? Bring that down. The Lagrangian with respect to our velocity in this position is simply just going to be negative, my bad, because it's minus, right? This one's simply just going to be mx dot. And then don't forget, in our Euler-Lagrange equation, we have to take the time derivative of this, right? So then d dt of partial L partial x dot is simply equal to this time derivative of mx dot, which is simply equal to mx dot dot. This should look familiar to you, right? And so our Euler-Lagrange equations state that dt of partial L partial q dot minus partial L partial q is equal to 0, or now we have mx dot dot minus mx is equal to 0, or x dot dot is equal to x. Or if we were to stay up here at this one, this necessarily becomes mx dot dot is equal to mx, or this is our familiar ma, right? Because the second derivative of your position is your acceleration, or our force. So technically up here we have our force equation, that the force or equation of motion for a harmonic oscillator involves this. And usually we put a k here for a constant, right? And you can solve this differential equation and you would see that it oscillates. Wow, it's an oscillator, right? And how do we know it oscillates? Because if we look at this differential equation, and this is physicists' favorite thing, I can take a guess, right? I see that I have a second derivative is equal to its first derivative, right? Dun, 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 dun. Those are our sinusoidal functions. Those are trigonometric functions, and those are like, our e to the ikx solutions, our cosine solutions. And I think in this case, it's been a while, but I think in this case, the solution that we would solve is that it's like cosine of omega t plus some frequency, probably times some constant. But solve it on your own. It's not that big of a deal. This is a solved problem. So, yeah, I think we'll call it there. Peace out, people.